Alright, what's up everyone? Welcome back to some structure free learning, and in this video we continue our mechanics of material sequence, and we're going to emphasize normal stress and shear stress in beams, but do it a little bit differently this time. Here we're going to be given material properties for the steel that's going to be used, and what we'd like to do is select the dimensions of this rectangular cross section of a steel beam given a simply supported condition with a uniform distributed load. And what we have to consider when we select B over here, this B and this H here, is that we want to consider the yield limit state in normal stress and the yield condition in shear stress. And this is what we call design, where we're considering limits for our structure or how we're going to fail and selecting a geometry based on this failure condition or this limit state. Another constraint that we have is that we want the rectangular cross section to have this height to width ratio of 2.5, which means that H is going to be 2.5 times B. Now the first thing I need to do is do some basic statics to determine the internal loading. My structure is a simply supported beam, so it's a pretty easy analysis. In this case I have a symmetric loading and symmetric boundary condition, so I know my reactions here are going to be equal. And in this case the resultant of this distributed load is 15 times 6, which is 90 kilonewtons. Like this here, this is going to be 90 kilonewtons, and because these are both equal I just have to divide that by half, so each of these is 45 kilonewtons. And from some of the forces in the horizontal, I would know that this force equals 0. And that's pretty easy. So once I have that, what calculating internal loading means is determining the internal axial shear and moments in a 2D problem. So we're just going to go ahead and draw the shear moment diagram for this. There's no internal axial loading. So here's my shear diagram, and it's a linear shear diagram. I go up 45 kilonewtons for that reaction, and then I'm decreasing linearly down to negative 45 kilonewtons at a rate of 15 kilonewtons per meter, which is the same as the uniformly distributed load of 15 kilonewton meters. And because my shear diagram is linear, I know my moment diagram is parabolic, and my maximum occurs where the shear is 0 here. And so this maximum value, the change in shear or the area here, is the same as my moment, this M max right here. And this M max is just equal to the area of the shear diagram, which is 1/2 base times the height. This intersection at 0 occurs at 3 meters. So this is 3 meters, that's 45 kilonewtons. And this gives me 67.5 kilonewton meters. And I want to know where my maximum moment and my maximum shears occur, because that's going to be where my maximum shear stress and my maximum normal stresses occur, as long as my beam cross section is uniform. So now that we have the internal forces and we have all these shear moment diagrams and things going on for our structure, what we want to do is look one limit state at a time and calculate what the dimension would be for that limit state. And so the first limit state that we're going to look at is the normal stress condition. And it doesn't matter. You can look at shear stress, normal stress, whatever, right? But just you got to look at them one at a time, and for each limit state there is essentially one basic design relationship, and some people call that basic design relationship a performance function. But here we're just going to call this we're just going to start by looking at normal stress yielding. And so here I have my normal stress, and we know that in terms of internal loads it's the moment that induces a normal stress on the cross section. So I'm going to go ahead, the maximum I'm just going to rewrite here at x equals 3 meters. We know that M max occurs, which is 67.5 kilonewton meters. And I'm going to go ahead and draw, just so that we can visualize what's going on, is I'm going to draw the normal stress profile due to the bending moment. So here's my cross section and generic normal stress profile. Notice the normal stress here is linear. The maximum normal stresses occur the furthest distance from this green line, this neutral axis here. So this is sigma max, and this would also be sigma max because my cross section is symmetric and the distances from the neutral axis are the same, except the bottom is in tension and the top is in compression. And the reason I know the top is in compression and the bottom is in tension is because I have a positive internal moment. This M max is positive, and in most cases and in most places, in terms of sign convention, an internal moment that's going like this, or making your beam into a happy face, it has compression at the top and tension at the bottom, and that's considered a positive moment here. Also, we know that the bending formula, or the normal stress due to bending, this sigma is equal to minus my over I, where I is the moment of inertia of the cross section. And this y is defined as the distance from the neutral axis upwards. We're going to utilize this formula for our basic design relationship. And really, you can tell already the moment of inertia is that one parameter in addition to this distance y that has the geometry of the cross section in there. And so here's this b and here is this h that we're really trying to figure out. Now, in more complex beam designs where you have maybe like an I-shaped cross section, you have to actually consider things like buckling in the compression zone and other kinds of limit states, like a plastic hinge if you're doing steel design. But we're not going to go there, right? We're just going to keep everything linear elastic, and first yielding is going to be considered our failure, or our limit state for this simply supported beam. And so our basic design relationship is as follows. For normal stress, it's sigma applied is less than or equal to sigma allow. Now, this allowable is defined by the engineer or by codes and factors of safety. Our limit state was yield, so here we have this sigma y, that's the material property, and then we want to have a factor of safety. We want to be a little bit more conservative than actually failing at yield, and so we had a factor of safety associated with yield that was given to us, and normally that factor of safety is prescribed by a code or something. The applied stress is going to be the stress induced by the internal loading. This M max is the internal loading. We want to know what that stress is that's induced by this internal moment. And so we're going to substitute here for sigma applied, M max times Y over I. And there's going to be a negative here, less than or equal to sigma allow. And in this case, sigma Y was 345 megapascal, which is 345 newtons per millimeter squared, over the safety factor from yield, which we said was going to be 2. And so this is going to be 172.5 newtons per millimeter squared. Alright, now that we have this basic design relationship set up, what we want to do is just substitute values and see if we can solve for a geometric quantity. And in this case, we're going to be solving for B, because we know that H is equal to 2.5 times B. So we're just going to make some substitutions. M max we found from the moment diagram. This was 67.5 kilonewton meters. The moment of inertia of this cross section about the neutral axis, which in this case is 1/12 base, times the height, which is 2.5 times B, quantity cubed, and Y is the distance from the neutral axis to the extreme tensile fiber or compression fiber, or in this case, wherever the normal stress is maximum. And so we can either choose the top or the bottom here. And if I choose the bottom, this distance is 2.5 times B divided by 2. So this right here would be 1.25 times B, and it would be negative because we're going down here. We're looking at this point right here on this cross section, which is downwards away from the neutral axis, and positive Y was defined as going upwards. And if I do some basic algebra, so the B's here cancel, bam, bam, right there, and I solve for B, what I'll get is B is greater than or equal to 0.072 meters, which is the same as 72, well, with the significant figure, 72.16 millimeters. And so that means in order for me to satisfy this normal stress basic design relationship, I need to have a width of this cross section, B, I'll call that B required, greater than or equal to 72.16 millimeters. So this is my requirement for the geometry based on normal stress. Now let's go ahead and try the shear stress. So the other limit state I want to look at is shear stress. And I know from my shear and moment diagram that the maximum shear force occurs at the supports, and that's going to be associated with my maximum shear stress. And I've set up the cross section here so I can draw my shear stress profile at the maximum shear force. And if my shear force is acting downward, the shear stress is distributed parabolically so that the intensity is parabolic with the maximum tau max occurring at the neutral axis. And what we'd like to do is draw or write out a basic design relationship for this maximum shear stress, which is essentially this tau max is tau applied. So tau applied less than or equal to tau allow, and this allowable is the yield stress, the shear yield stress of the material divided by the safety factor or factor of safety. And in this case, we'd have tau applied less than or equal to 207 megapascals divided by the safety factor of 3 from shear yield, and this would be 69 megapascals, which is newtons per millimeter squared. And for tau applied, I'm just going to substitute the equation I would use to calculate this maximum shear stress as tau max. This is going to be this VQ over IT less than or equal to 69 newtons. I know V, I know I know how to calculate I. That's 1/12 base times height cubed. T is going to be the width at the location where I'm calculating the shear stress. So it's this location right here, which is just B. And Q is the first moment of area, which I have to calculate. So this Q is equal to the sum of A prime times Y bar prime. This Q is all the area above where you want to calculate the maximum shear stress, or all the area below. And so if this right here represents my area all above, the centroid of this would be Y bar prime. And in terms of H and B, or just in terms of B here, this whole thing just comes out to this area, which is 1/2 base times the height, which is 2.5 times B. This Y bar prime is, let's see, this distance right here would be 2.5 times B divided by 2, and this is B divided by 2, so Y bar would be 2.5 times B divided by 4. This would be 2.5 B divided by 4. And I would take this whole Q right here and just substitute it into this right here. And if you believe everything that I've told you so far, if we go ahead and do some basic algebra and work out some numbers, it's going to look like. And so this is what the basic design relationship looks like, with all the numbers substituted in and everything in terms of B here. And when I go through the algebra and I solve for B, I'll get B required associated with the shear yield limit state. B required greater than or equal to 19.78 millimeters. So in summary, I have here, based on the limit states that I looked at, for normal stress, I need a width of 72.16 millimeters for my cross section. For shear stress, I need a width of 19.78 millimeters. So what me as an engineer, I've got to choose the requirement that satisfies both criteria. And in this case, it's rather obvious. It's the largest of the two here. And this B required is going to be greater than or equal to 72.16 millimeters. And obviously, as an engineer, I cannot choose 72.16 millimeters because they don't make it like that, right? You're not going to cut everything to exact size, otherwise you would be a really inefficient engineer. And so what we would specify as a designer, hopefully B design, that we would choose is something that they make, probably something like 75 millimeters. And H, the height required, would be greater than or equal to 2.5 times B required, which would be 180.44 millimeters. And that would mean that I would choose something that is also fabricated, or maybe I might choose 2.5 times 75. So here, H design would be 187. And so I might specify a cross section here that has these dimensions as my final design to satisfy the loading and the safety factor and material properties that I'm using. Alright, and that's it. I hope that was an insightful use of the bending formula and the transverse shear formula. If you have any questions, let me know. And you know what I'm saying, keep it structure free. See ya.